Most of the decision trees suffer from a problem called overfitting. So what exactly is overfitting? So let's try to understand the problem of overfitting by going through a quick example decision tree. So we'll use the buyer profiles data, we'll fit a decision tree on it, and then try to observe what exactly is overfitting. So we need to import both test and training data. So first we need to build a decision tree model on the training data, then find the accuracy on the training data. Now the test data is similar to training data, that is just to see how accurate our model is on a different data set, like on a similar but slightly out of time data, which is not exactly same as training data, but it belongs to the same population of buyers. We just took some data outside from the model building population, and then let us see what is the prediction on the prediction accuracy on the test data. So first we need to find the accuracy on training data, then we have to find the accuracy on test data using the same model that we built on training data. Let us see how it is done. So first will try to get test and training data. So both of them are imported, test data and training data, and then we'll try to build a decision tree. So let us see the training data. So we need to build a decision tree on the training data. So let us see the head of training data. It has age, gender, and whether a customer has bought the product or not. Okay, yes means bought the product, no did not buy the product, age, some values, numerical values, gender, male, female. Now let's try to build a decision tree to predict buying pattern based on profile variables like age and then gender. Okay, then method is classification method, and then control minimum split to, like that we have mentioned all the parameters. So we will try to build a decision tree. So you might have observed controlled min split is 2 because there are very few observations we can afford to give like this. Let us give min split equal to 2 and see what is happening. So let's try to build a decision tree here. So I have built a sample tree. You can see the sample tree here. So this is the tree that we have built. It has a root. I think an easy way to understand, as we do every time, let's try to plot the tree. So when we plot the tree at the root level, how many observations are there? Then first of all, it is divided by gender. Female customers, most of them are not buying. Male customers, yes, they are buying. Within that again it is splitting it based on age greater than 20, no they are not buying. Age less than 20, no they are again not buying. Again within that there is a specific segment of buyers within age greater than, age less than 20, age less than 12 or 11.5, they are not buying. If we try to understand this a bit closely, let us look at the actual output and what each final node is talking about, the leaf nodes. So the fourth one is a leaf node. So if we have to traverse this path, then we have to come through gender equal to female, gender is female, and age greater than 20, then they are not buying. Looks like a pretty straightforward condition. If you see any new customer, if their gender is female and age greater than 20, then no, they are not buying. If gender equal to female and age less than 20, that is this one, and age less than 11.5, this is actually 11.5 rounded off to 12, so then also they are not buying, that is the 10th node, so they are not buying. So it is as good as saying gender is female and age actually less than 11.5, because anyway it is less than 20. So gender is female, age less than 11.5, they are not buying. Now gender is female, age is less than 20, but age is also greater than 11.5. That means age between 11.5 to 20, between that there are few buyers. So when they are female, they are not buying. Within female, age less than 11.5, not buying. Within female, age greater than 20, not buying. Within female, age between 11.5 and 20, yes, they are buying. Okay. Similarly, male population, age greater than 47, so that is the node. Age greater than 47 is this node. Within that again, age less than 52, this is the one, the 12th node. So male, age greater than 47 and age less than 52, they are non-buyers. Within male, most of them are actually buyers, age greater than or equal to 47 and age greater than or equal to 52, which is as good as saying age greater than 52, yes, they are buyers. Within male, age less than 47, they are again buyers. So the only segment which is coming as non-buyers is especially those customers whose age is between 47 and 52. Only those 5 years of customers, like customers within that age group, they are not buying. Looks like everyone else, like in male population, are buying. Similarly, in the female population, there is a specific age group they are buying. There are other age groups they are not buying. Looks like a very complicated tree with very specific intervals for age where some people are buying. Now let us see the accuracy of this model that we have built. What is the accuracy of this model? Let us validate. So let us do the predictions on this model. So these are the predictions. Let me create the confusion matrix. So the confusion matrix says that whenever it is no, whenever actually is no, we are predicting it as no. Whenever actually is yes, we are predicting it as yes. In fact, there are no non-diagonal elements, so we have 100% accuracy, 100%. There is no misclassification error at all. This model is 100% accurate. So that is what we can say. This is one of the best models. But is it really the best model? That is what we need to test on the test data. Test data is just a data which is kept apart. We did not use in model building, but the customers who are actually in this particular data set, they are very similar to those customers. So let us use the same model, that is sample tree, but this time we will use to predict on the test data, not the training data. Then see what is the accuracy on the test data side. Also we know what are the, whether a customer has bought or not bought, but we just want to see how well our model performs. When age is given, when gender is given, we are saying that we are 100% accurately predicting whether a person will buy or not. Let us see how our model will predict on the test data. Okay, at least we expect, if not 100% accuracy, at least we expect 90% or 85 to 90% accuracy on the test data. So predictions on the test data, this is the code for predictions on the test data. Then the confusion matrix on the test data. Whenever it is yes, are we saying yes? So whenever it is no, we are saying no only once. Whenever it is yes, we are saying no thrice. So looks like our model is not really doing good on test data. Actually actually the accuracy of our model is only 33%, and the misclassification error is 1 minus accuracy, that is almost like 66%. So our model is really good on the training data, but performed really worse on the test data. Looks like what we did in our model is we fit a model that is perfect for our training data. We overfit the model. What did we do? We took the data and we kept on increasing the tree size so that the tree is kind of almost defining each row as a rule itself. I mean, if we grow further, the tree might even say that if age is 29, gender is male, then they'll buy. If age is 34, gender is male, then they'll buy. If age is 13, gender is female, then they'll buy. If we further grow, we might even see each row as a rule itself. Now that is a problem. So that is called overfitting. Like, when you overgrow the tree more than a certain complexity level, then there is an issue of overfitting. What is overfitting? The model is super good on your training data, on the data that is used in building the model. It will have 100% or 98% accuracy, but when you take with small variations, when you take test data, okay, which is similar to training data but with very small minor variations, when you try to test it on the test data, you will see the accuracy go really low. That is the problem of overfitting. Generally overfitting happens when you really grow the tree like very big, generally large. I mean, the trees which are having large depth or height, they will actually suffer from the problem of overfitting. That's what I mean. Instead of finding a general rule that okay, age greater than 50 buyers, age less than 50 non-buyers, instead of finding a rule like that, what rule we are finding? We are doing that okay, age from 27 to 29 buyers, from 28 to 20. I mean, by mistake or it can happen that there are some non-buyers within a particular age range, which is fine. But if we still try to model even such certain random variations in the data, then we run into the problem of overfitting. The final model should not be exactly the same table that we are actually using it as an input. I mean, the final decision tree cannot be the same input table that we just gave. In that case, we are not achieving anything as a model. It can't be used for prediction. So that's called the problem of overfitting, which an analyst need to be very careful while building the model, a decision tree model. We need to make sure that we don't we should not commit the mistake of overfitting. So we have already seen that growing the tree beyond a certain level of complexity leads to overfitting. That means instead of actually finding the general rules for the target buying or not buying, using the variables, input variables, we are actually trying to represent the whole data as itself. Now that is overfitting. When overfitting happens, the model is really good on training data, on test data, it really fails. Now what we need to do, we should not grow the tree as big as possible. We might have to cut it beyond a certain level of complexity. Okay, we might have to trim the trees after building them, or at least we need to control the tree growth before building them itself. Before building the tree itself, we might have to say the decision tree algorithm that okay, do not build beyond this level of beyond this level of complexity. Do not build if the information value is not much improved. Do not build beyond 3-4 steps. Okay, so or if you already built, maybe we might want to prune the tree. So the process of trimming the trees is called pruning. So we are building the decision trees and we don't want to grow them as big as possible. We want to build smaller compact trees. This process is called pruning. Okay, pruning obviously helps us to avoid overfitting because we are not really growing the trees really big. That's why obviously it avoids overfitting. Generally we always prefer to have a simple model. Generally simple models avoid overfitting. When the model is simple, you are not actually specifically building the model for each observation in the data. any additional split that does not add any significant value to our prediction, then it doesn't really make sense to grow the tree. Okay, now in R, with it is very specific, like we can use a complexity parameter to control the tree growth. So there is, while building the tree itself, in decision tree R part algorithm, in control, like the way we give a minimum split number, we can also give complexity parameter, which will help us to prune the trees, or which will help us to stop the growth of the trees, so that we can avoid overfitting. So in R, we can set the complexity parameter to prune the trees, or to use as a stopping criteria to actually not overgrow the trees, or to avoid the overfitting. So complexity parameter used to mention the minimum improvement before proceeding further to grow the tree. So it's like this. So imagine, before splitting a node, the overall error is a certain percentage. Let's say if it is a 50% error is there, and after splitting the node, the error reduced a lot and it became 10%, then the split is really worthwhile. Now before splitting the node, the error is let's say 50%. After the split, the error is 0.48, or let's say 48%. Then that is not, that split is not really worthy. So that is where we actually can mention complexity parameter, which is denoted by CP, and we specifically say that if there is not this much of improvement, let's say if there is not much, like 10% improvement is not there, then do not grow the tree. If there is if at least 5% improvement we are looking for at each node, if overall error is not reduced by 5%, do not grow the tree. So that's what we can mention in R using complexity parameter. We'll see an example anyway. So basically, the complexity parameter tells the decision tree that before splitting any node, before going further, make sure that the split is actually helping the model to increase the accuracy or reduce the overall error. Okay, it can be used as a good stopping criteria. In fact, it can be compared, or it is analogous to adjusted R square. You remember in regression analysis, we use adjusted R square, where there are places where R square fails in multiple regression, where if we keep on adding the variables, the R square value increases, but adjusted R square value increases only when there is a significant contribution of the new variable. Otherwise adjusted R square decreases. So it is kind of similar to adjusted R square value, but not exactly the same. The complexity parameter tells the tree, or it does a good job of cutting the tree beyond, so that tree doesn't grow beyond a certain limit. Okay, the default value of complexity parameter is 0.01. We can adjust it to higher value or lower value that will suit our model. In fact, we will see how to actually select the complexity parameter later. Now let us see an example of changing the complexity parameter, how it is helped in avoiding overfitting, and it prunes the tree. So we are going to take the same training data, same model that we have built earlier. It struggled with overfitting. It has 100% accuracy on training data. On test data, it failed miserably, the model. Now we are building a different model, but this time in control I am mentioning CP as 0.1. That means if there is not as much as 10% improvement in going to your next step, do not grow the tree. You cut it wherever it is. If there is if from a node to next level, if there is not much of 10% improvement in the accuracy or error, then do not go beyond that. So that is the code. So everything remains the same. Just after minimum split in RPAT control, I just mentioned the complexity parameter as 10% 0.01, but this time I'm building sample tree 1. Now I can print sample tree 1. Looks like just it has 2 jail nodes and 1 root node. Looks like it's a just a small tree, and actually it is cutting the whole tree at gender itself. Age doesn't have any significance. Splitting this beyond gender is not improving the overall accuracy much. That is why it just stopped here. Now we might not have 100% accuracy, but we should be having decent accuracy on training data. Now let us see the accuracy on training data. So these are the predictions on training data. This is the confusion matrix. Yes, obviously there are some errors, but most of them are accurate. And then this is the accuracy. Accuracy is 85%, 85.7, which is fairly good. Now what we are really testing here is what if I use the same model on the testing data, do I get same 85% accuracy? I mean, if I'm getting like really lesser than 85, then the model is not really powerful. At least if we are getting slightly in and around 85, less than 85, like 83 or 80 is still good enough. 80% or more is good enough. So let us find the predictions on the test data. Now let us build the confusion matrix on the test data. The confusion matrix says it looks quite good. Most of them are diagonal elements, and the accuracy is 83%. So that is how we can use complexity parameter to mention the growth of the tree, to actually tell the tree that do not grow beyond this complexity, or do not grow if the accuracy is not increasing more than this much, or do not grow if the error is not reducing by just growing the tree. So that is how we can use the complexity parameter in R. Now how do we choose complexity parameter? Let us see how do we choose the complexity parameter. So how do we choose the complexity parameter? Is it 0.1 all the time? Is it 10%, or is it 5%? Or depending on the tree, does the complexity parameter increase or decrease depending on the data? So how do we actually choose the right complexity parameter for a given decision tree, and make sure that we are not building a tree that is very weak in itself? I mean, just to avoid overfitting, we should not build very simple tree so that it doesn't even have minimum required accuracy. Just to avoid overfitting, we should not fit a model that is just 60% accurate or anything. So we need to choose the complexity parameter little smartly. Okay, so how do we do that? So we can actually choose the complexity parameter by analyzing the cross validation error. If you remember, the test error that we are talking about, that is nothing but the cross validation. It's an example of cross validation. That means instead of using the training data, we are taking a different data set and then cross validating the error. So whenever we are building a tree, whenever we are building a new split, we expect the test or the training error to reduce. We expect the error to reduce and the accuracy to increase. If the same thing is happening on cross validation also, even the cross validation error is also reducing at every split, then it's a good split. But at a split, if the cross validation error is increasing, actually that means we are trying to overfit the model to the training data, and on the test data the error is actually increasing by doing by adding one more split. So that is how we can actually decide the cross we can decide the complexity parameter CP. So we can do actually two types of prunings. We can do pre-pruning by mentioning the complexity parameter in the beginning itself, or we can grow the entire tree, then we can actually prune it. That is called post pruning, because we have already grown the tree, and whichever branches we don't require from that node onwards, we can actually prune it in from the bottom up fashion. Okay, so first of all, let us see how do we choose the complexity parameter. So we can actually use print cp. Print cp prints the values related to that particular tree, and we can also see the error, the training error and the cross validation error at each of the nodes. So sample tree, the bigger tree that we saw, if you remember the sample tree, that was the overfitted model that we are talking about. Now when we do the print cp of that one, the major table that we need to focus is this one, in that we are given the complexity parameter. This is at the root level, this is at the second node level, and then the third level it has actually 5 splits. So the error at the root is 1, and then the error reduced to 28%, and the end the error was 0. If you remember, in that tree there was almost like 0 error. That's what we have seen. But the cross validation error, in the first case it reduced, right? But then when we go further down, the cross validation error increased. So that is when we would say that, oh, I mean, there is no point in actually going further. The complexity parameter can be set anywhere around 0.7, so that we can just stop the trees in the second level itself. You can see from the graph also, you can draw a graph for the complexity parameter or cross validation results. You can draw a graph by using plot cp, plot complexity parameter. So plot cp gives us this graph. In this we can see that as the complexity parameter is increasing, the cross validation error is actually increasing. You have to read this graph from right to left. Complexity parameter very low, then complexity parameter little high, and complexity parameter is infinity, right? So the size of the tree is 1, complexity parameter is almost like infinity, that it is not defined. When the complexity parameter is 0.23, the actual error reduced. When the complexity parameter is even lesser, okay, when the complexity parameter is 0.027, that means by splitting the node I'm expecting very less improvement, almost like 2% improvement. That means I'm not going to see not much of accuracy in the test data. So it's better to choose the complexity parameter, or it's better to cut the tree at the second level itself. We don't need those many nodes. So the way we do it is, we built a different tree, sample tree part 2, then we take the training data, then in R control, R part, in control I will give control as 0.23, so that I'll just break it at second level itself. So I'm building the second tree. So in that I'm just stopping at here itself, because going beyond this is not going to improve our model at all, because the cross validation error is increasing if I reduce the complexity, or the complexity parameter is nothing but improvement in the error, or improvement in the accuracy, or reduction in the error by giving a new split, or by expanding the tree. If the error is not improved much, or if the accuracy is not improved much, if the error is not reduced much, then there is no point in further drilling it down. So that is what we are saying. If there is not much of improvement, if the improvement is less than 23%, then we'll not go further. That's what we have mentioned. But earlier it was taking, even if there was a 2% improvement also, the tree has gone ahead and built. But now we have actually stopped it. If it is at 20%, you have to stop it and then go ahead, I mean just stop the tree building and release that, or result it or output the tree as it is by stopping the growth of the tree at a complexity parameter of 0.23. So let us see the sample tree. We can see that the second sample tree is just stopping at gender equal to female and gender equal to male. Just at gender you can also draw the same one. Simply we are stopping it at the second level itself. Previously we have seen pruning the trees using the complexity parameter CP, so that if we mention the complexity parameter CP value to a limit, whenever a split is not giving a real good improvement in the accuracy or error is not very well reduced, then the tree will be pruned at that point, till that point. There are actually two types of pruning. One is pre-pruning. Whatever we have seen till now is pre-pruning. We mentioned the CP value while building the tree itself. So while doing the algorithm, while building the tree itself, the decision tree will be cut to a minimal level. Now there is something called post pruning, where we grow the tree to its entirety. That means we grow the tree as big as possible, or but unfortunately or fortunately we have built the decision tree already. Now later we thought that it's too big and we want to prune it now. I mean, after building the tree we have realized that we have overfit the model, we want to prune it. Then in that case we can do something called post pruning. We can input the tree and trim off some of the nodes. So let us see how to do post pruning. So let us take this example of this is a sample tree where we are building it as big as possible. So this is the sample tree. As we have already seen that this is a overfit tree, because age doesn't really have any impact, but still we see so many nodes split based on age. So this is clearly a tree which has already grown more than its necessary size. Now we can actually plot the value, we can actually see the tree and we can prune it using a function called prune, prune, and we have already seen that the value of CP can be cut at 0.03. Earlier, I mean, if we would have been building the tree, we have mentioned the CP value to be 0.03. Now if I want to prune this tree, I will use the function called prune. I'll enter the tree that I have, that the bigger tree, and I can mention the value of CP as 0.23. Now that will create a pruned tree, and we can print the pruned tree and see the value. So this is the pruned tree, and you can see the plot of the pruned tree, which is exactly same as the tree that we have built it earlier. So earlier we have built a pre-pruned tree. Now this is post pruning example. Now let's put all of our learning together. We have learned about decision trees, we have learned about validation of decision trees, we have learned about cross validation, pruning, etc. Now let us see how to actually take one business problem, apply the decision tree model, and build the final decision tree prediction model that can be used for predicting or classifying the target variable based on some of the predictor variables. So here is an example. Again, we'll talk about fiber bits data. We have already used this example in logistic regression. Some of the results that are coming out of this model can be also compared with logistic regression model as a benchmark. So import the fiber bits data. So this is internet service provider data. If you haven't already worked on logistic regression, it is fine. You can simply ignore it, treat this as an independent example. So import the fiber bits data and its internet service provider data. Some of the customers have iterated, some of the customers are still using that internet service provider services. Now there are some independent factors like speed of the internet, service quality, etc. Based on that, we need to predict whether a customer will iterate or not. So we need to classify the whole data as iterate and non-iterate, so that next time, or the customers that are already existed in our portfolio, we can actually find the probability of attrition in next few months. If we can find and identify such customers, we can actually run some campaigns, or we can float some offers to those customers so that they'll stick back to the same service provider. That is what the overall idea. So what we need to do to classify these customers as attrited, non-attrited, we need to build a decision tree model. We have to prune it if it is required. We have to do the final accuracy and validation statistics. We also need to identify, is there any 100% active or inactive customer segments. That means, are there any segments, are there any characteristics of customers based on which we can say yes, these customers will be definitely active, or are there any specific characteristics of the customers based on which we can say they will be definitely going to be inactive, or they are going to be attrited soon. So let us try to build a decision tree model on fiber bits data. So here is the fiber bits data. Let's clean up a bit. Let's clean everything. So let's get fiber bits data. Yep, it has around 100,000 observations, 9 variables. We can see the names of the fiber bits data, active customers, that is the target variable, and then customers income, months on network, number of complaints, number of plan changes, relocation status, monthly bill, technical issues, speed, test result. Based on all these variables, we need to find out, or we need to classify the customers as active and inactive. So we'll try to build the fiber bits model using our decision tree algorithm. rpart is a package. Using rpart, I want to say active customer is what we want to predict. Using rest all the variables, we can just put a dot there. Method is classification. rpart control, minimum split size is 30. cp value, we can give it anything right now, or we can simply ignore it, but let us give slightly lesser cp value later on. If we require, we can prune the tree. Data set is fiber bits. So let us build this tree. It takes some time. There are 100,000 observations. Now this is the fiber bits tree. Oh, this looks like a really big tree. Let us try to draw the tree. Since there are so many nodes, I think it is taking some time to actually create this whole tree diagram. Looks like, yeah, it's finally done, but these are very small, too tiny to interpret. Looks like we have mentioned the CP value too low. Okay, we might have grown the tree more than its capacity. Maybe let's see whether we can do something with print CP to look at the CP value, to choose the CP value. Yes, maybe a better plot to look at that is the table, this same table along with the combination of plot CP. Yes, so looks like after this point, okay, or after this point 0018, there is very less improvement. Almost this is flat. Okay, after this complexity, the error rate is not really improving. Okay, earlier, like if I would have had complexity parameter here, if I would have actually cut the tree at 2 nodes itself, then the error would have been higher. Like if I grow it still till 3 nodes, then error reduced, right? Error is 60%. So when the tree size is around 16 or more, I think the error is not really reducing. Till 16 the error is reducing. So earlier the error at the root node is 100%. Now at this node error comes to be somewhat around around 20%. It is just going on. I think it's around 30%, I guess. But one thing is very clear, that beyond this particular node, beyond these 16 nodes, it is not really improving. We can we can take a cutoff value of CP as 0.0018 to start with. So let us prune this tree. So earlier we have bit 5 bits tree. Now let us prune it at this point. This can be also seen here at 13, around this bit. So we will take this value 0.0018631, so at node 6. So we will take, let us take only 8 nodes, 8 splits, and then cut off the remaining trees, because it is not really improving the cross validation error. You can see the cross validation error kept on decreasing, but after this it is not really decreasing that much. So I'm building fiber bits tree 1. I'm pruning the earlier model fiber bits tree, and we are cutting it at 0.0081631. Earlier we have put CP value as 0.001. Now we made it as 0.008. Still looks like a big tree, but it must be smaller than the earlier tree. So this is the tree. So relocation status, then the next variable is speed, test result, then the next variable is technical issues, number of plan changes, etc., etc. Again we will still validate this. We will print CP values, complexity parameter, and the out of validation error, cross validation error. It reduced and then further reduced. Maybe if we really want to cut it, maybe we can choose this CP value as 0.23916, and still, like, if we have a feeling that cross validation is error reduced from 41 to 37, if we don't really care about this, we can simply cut off at CP value this, or I think it's okay to keep these nodes, and looks like all these can be kept. This looks like a good stable tree. Or if we still further want to reduce, we can actually give CP as 0.0023. So let us build a different tree, that is fiber bits 2, by pruning fiber bits tree, the first one, choosing the CP as 0.0023, and let's draw the final plot. Yeah, we just cut down before one node, and these are the values. We can again see the print CP values. They're nothing but the same one. So cross validation error reduced from 0.75 to 0.58 to 0.04 and 0.41. So it's up to us where we want to cut down. We can debate this again and again and choose the right tree. I would say choosing tree 1 itself is not a bad idea. One can choose this tree 1 itself, or we can even go ahead, if we want even a simpler tree, we can choose tree 2 also. So let us choose tree 2. As I told earlier, choosing tree 1 is not a wrong choice at all. CP value of 0.00181 is fine, good enough. Now let us suppose you choose one of the trees. Now finally we will create the confusion matrix and see the accuracy of this particular tree. I am creating the confusion matrix, and the accuracy comes out around 82%. 82% is the accuracy of this particular tree model that we have built. We know how to predict. We have to use the predict function, and you mention the variable values, the list of variable values, then finally the output will come as positive or negative class. So the final model, if somebody really asks us what exactly is the final decision tree model, we will call this, we can print this model. This is the final decision tree model. We want it to be slightly simpler, that's why we chose this model. Now how do we interpret this model? We have already seen how to read a tree model. So this is the tree model. Go to the nodes. So the second node itself is a leaf node. So whenever relocation status is more than 0.5, I think relocation status is yes. Whenever relocation status is yes, then most of them are actually 0. So 0 means those who have left the internet service. So whenever relocation status is yes, whenever somebody relocated, they are turning out to be inactive. Most of them, in fact 92% of them are inactive whenever relocation status is yes. And another root node, another leaf node is technical issues per month. Whenever technical issues are higher, and that is again coming from speed test result. Whenever speed test result is lesser and then technical issues per month are higher, then also people are leaving. 73% of the people actually left the internet service provider whenever technical issues are high, speed is also not good, then they are leaving. Only people who stayed back are 26%, and there is a good chunk of population. There are 22,000 such customers. Out of them, most of them left. 73% of them left. Why did they leave? Because technical issues are higher. Speed test result shows that they're not getting good speed. Who are staying back? Let us look at some positive segments. So one way to solve this business issue is maybe technical issues should not be there. Speed test, maybe whenever we see that a new customer in future, anyway these guys are left, in future if we see that a new customer is facing a lot of technical issues, and if his speed test results are, he's not getting good speed, we need to make sure those customers are actually taken care of before they leave the service. Before they actually leave our company, before they choose some other internet service provider, we need to identify those customers whose speed is low, whose internet speed is low, or we are not able to provide them good speed, and there are so many technical issues for such customers. We might have to give some kind of incentives to keep them back. And there are some customers who are actually who are staying back. Whenever customers whose technical issues per month are less than 3.5, whenever there are only slightly lesser technical issues, they are staying back. So one learning from here is that you should not have a lot of technical issues. You should not have internet outages, then only customers are staying back. Maybe an improvement area there. Now income also has can be interpreted in the same way, and then speed test result looks like it's a very important variable. Okay, that is how we can interpret this decision tree and find out the reasons for customers leaving, or at least find out the customer segments or concentrated customer segments which are staying back, or concentrated customer segments which are attriting.